So in this video, we're going to look at the index of refraction. In particular, we want to look at the numbers that you will see if you look them up in a book. And when you look at the values in a textbook, you will see differences based on what kind of material, what kind of crystal system the materials are, where the values are being listed. So we have things that are isotropic. Things that are isotropic belong to the cubic, or equivalently the isometric system. Remember, isometric means equal measure. Isotropic is similar. It means that in terms of the index of refraction, the value of n, remember that reflects the velocity of light, or the inverse of the velocity. For isotropic, velocity of light is the same in all directions. So for a cubic or isometric system, you will have three axes. We would normally call them A, B, and C, but if they're all the same, we just call them A1, A2, A3, because there's really no difference between the two. And if light travels along the A2 direction, or along the A3 direction, or along the A1 direction, it really doesn't matter. It'll all move with the same velocity. Whereas if you have an anisotropic mineral, then what happens is that light will move differently. Let's say we have something with distinct A, B, C axes. So light might move a little more quickly or slowly along A, and it'll move differently along B, and then maybe differently along C. And so if you have three distinct crystallographic axes, you'll have three distinct values for n. Now those values, those axes, the directions along which that light propagates, they might not exactly match the crystallographic axes, but they will be affected by those. So let's clear the chalkboard and look at some examples. If we look at the mineral fluorite is isometric, and there is only one value of n, and depending on the book you look in, you'll see something like 1.4338. So that is the inverse of velocity of light through the mineral fluorite. There's only one value because it doesn't matter which direction light is propagated, it'll always move at the same velocity, so we only get one value of n. And in fact, this is really the only optical property for this mineral. We'll talk about a number of other optical properties. This is the only optical property for fluorite, its index of refraction. But if you look up quartz, quartz is hexagonal. Now with hexagonal crystals, we have a distinct C-axis, but then we also have distinct A-axes, and there are three of them. There's an A1 that's front to back, A2 left to right, and then A3 that's kind of at an angle. So there they are. The index of refraction for A1 will equal that of A2, and that will equal the index of refraction for A3. So all those will be the same, but none of them will be the same for propagation of light along the C direction. So when we take a look at quartz, let's clear the chalkboard again. You'll see two values listed. You'll see an n omega that'll be listed at something like 1.5533, and then you'll see an n omega that is about 1.5442. I don't know if I misspoke here. This is epsilon. And in a British textbook, they might drop the n and just call it epsilon. So instead of n sub epsilon, it'll just be the epsilon itself. Over here, same thing. The British convention, they might just call it omega without the n, although in American textbooks, we usually use the n and then the subscript. We get two different values that reflect that range, and if light is being propagated in some direction that is in between the C and A axes, then you can have some value that's in between. So you can have anything from a low of 1.5442 to a high of 1.533, and anything in between. That would all work. Let's take it another example. So let's say we have the mineral Aragonite. Aragonite, you'll see three values, an N alpha, which is about 1.5301, and then an N beta, which is 1.6816, and then an N gamma, which will be about 1.6859. So we have a low here and a high of this value here. This represents the three different crystallographic directions in which light can be propagated. Again, those won't necessarily match precisely the ABC directions. They could be different, they could be the same. In Aragonite, they will be different, but we will have a range of values for n, from a low of 1.5301 to a high of 1.6859. single mineral of a single composition. It could be pure CaCO3, but depending on the way light is being transmitted along the A, B, or C directions, we can have different values for the velocity and therefore different values for n. So to sum up, if we have something that is in the cubic or isometric system, then the number of values of n is just 1. That's the only optical property. If you have hexagonal or tetragonal minerals, then you have 2 distinct optical propagation directions, so you'll have 2 values of n. And then for everything else, orthorhombic, monoclinic, and tetragonal, all of the minerals that fall into those systems, you'll see 3 values of n. This will just be called n. These will be listed as epsilon and omega, and these will be listed as alpha, beta, and gamma. And so you'll see these in various conventions, sometimes just the regular epsilon, sometimes n with a subscript, depending on whether it's a British or American convention. Very sloppy epsilon that is supposed to be this guy here. But these are the values that you'll see, and we'll talk about these in another video when we talk about relief, and then some other videos where we will discuss Becky line.